This session is dedicated to discussion of physical interpretation of the gradient of a scalar field phi. So suppose we think that a scalar field phi as describing the temperature throughout a region, then this temperature varies from one point to another point. So at any particular point, then it can be shown that the gradient of phi is a vector pointing the direction in which the rate of temperature increases, or in the direction in which the temperature increase is greatest. So if we define the magnitude of the gradient of the temperature function phi, then we determine the increase in that particular direction. So let's give the definition here. So suppose that our scalar function phi describes the flow of temperature in a region, but then obviously the temperature varies from point to point within the same region. So at a particular point, it can be shown that so this is the key point here, that at a point within this region, then the gradient of this temperature function can be shown to be pointing in the direction in which the rate of temperature increase is actually greatest. Now, if you define the magnitude of this vector. So the magnitude of the vector pointing in the direction in which the rate of temperature increase is greatest defines the magnitude or size of this rate of change. So similarly, now you negate the gradient of this temperature function, then you get the rate of temperature decrease that is greatest. So these similar interpretations can be given to other scalar fields. Now suppose that the electrostatic potential is given by this function. So an example, suppose so this function v equals to y over x squared plus y squared plus z squared raised power 3 over 2. Given that So there's a problem that suppose that an electrostatic potential V in a region is given by this function, and that a unit charge is located at the point with coordinates 2, 1, 0 in this given region. Find the direction at this point in which the rate of decrease, so the key word here is decrease, is greatest. So then the first thing to do is to define the gradient of this electrostatic potential. And once we have defined the gradient of the electrostatic potential, we find its value at the point 210. And then once we have the value at the point 210, then we will negate that gradient, that vector, because we are interested with the rate of decrease. If we are interested in the rate of increase, then we'll leave the answer in positive form the way it is. So solution. So gradient of V is the same as partial x of V I plus partial V partial yj plus partial V partial zk. Please note that electrostatic potential is a scalar quantity or a scalar field. That's why there's no arrow on this vector, on this letter V. So this is a scalar. So that should be noted well in advance. Now, this function V may be written as, so V actually can be written as y into x squared plus y squared plus z squared raised power minus 3/2. So partial V partial x will be given by, now this one using chain rule, differentiating, so I'll have to drop 3/2, and then I'll have x squared plus y squared plus z squared. Now subtract 1 from the power I have minus 5/2. And then there's y here. And then when you differentiate inside with respect to x, you get 2x. So this will reduce to minus 3xy, because these 2 and 2 will cancel out. So I have x times y, x squared plus y squared plus z squared raised power minus 5/2. And then partial V partial y. Now this one I'll have to use product rule because this is y, and then this part also has a y. So this will be my V. So u prime is 1. So I'll have times V will be x squared plus y squared plus z squared raised power minus 3/2. And then plus V prime, but I have negative because I have to drop this power. So I'll have 3/2, then y. And then when I differentiate inside, I get 2y, and then x squared plus y squared plus z squared power minus 5/2. So this will give me x squared plus y squared plus z squared raised power minus 3/2. So this will be minus 2 and 2 cancels out. So I'll have 3y squared into x squared plus y squared plus z squared raised power minus 5/2. And then partial V partial z I'll have, so using chain rule on the brackets, I'll have drop minus 3/2 and then times y. If I differentiate inside, I get 2z. Then I have x squared plus y squared plus z squared for minus 5/2, which will be minus 3yz into x squared plus y squared plus z squared for minus 5/2. Now, actually, I can evaluate the values at the point specified, 2, 1, 0. So I mean, this means that where this x I replace by 2, so I'll have minus 3. Where this x I put 2, where this y I put 1. X is 2 squared plus 1 squared plus 0 squared raised to minus 5/2. This will give me, so this is minus 6 into 2 squared is 4 plus 1 is 5 raised to minus 5/2. So this will give me minus 0.10733.12629. And then partial v, partial y at 2, 1, 0. I'll get 2 squared plus 1 squared plus 0 squared raised to minus 3/2 minus 3 into 1 squared into 2 squared plus 1 squared plus 0 squared raised to minus 5/2. And this will give me 5 raised to minus 3/2 minus 3 into 5 raised to minus 5/2, which will give me 0.0357708,764. And then partial v, partial z at the point 2, 1, 0 will be minus 3 times y is 1, and then z is 0 into 2 squared plus 1 squared plus 0 squared raised to minus 5/2. The fact that we have a 0 here, then this will be 0. So therefore, the gradient of v at 2, 1, 0 will be given by minus 0.10733.12629 I plus 0.03577708764J plus 0K. So this is the value of the vector which showed the rate of increase in potential, which showed the direction in which the rate of increase in potential is greatest. But the question was to specify the rate of the vector which showed the rate of decrease of potential is increasing or greatest. So therefore, the rate direction of rate in which or rate of a decrease in potential is greatest is negative of this value, which is given by now. This will be positive and this negative. So note that if they had asked us to find the magnitude of the direction where the rate of decrease is greatest, we'll simply get the magnitude of this vector. So that is how we interpret gradient of a scalar function in physical nature for the case of an electrostatic potential, or sometimes you can do the same interpretation for pressure, and you can as well do the same interpretation for temperature. Thank you.